say shear modulus or rigidity modulus is given by shearing stress by shearing strain. What we said as in the last session, what can be written as F by A into theta or F A into theta. F A into theta. Or you can also write as we have written in the previous class. So if this is the shape, then this is X, this is H, this is theta. Then theta equals X by H. Therefore, we can simply write rigidity modulus as Fa X by H or Fh by Ax. That is the thing. So this is the idea of say rigidity modulus or shear modulus. Next, we go for bulk modulus. It is there in the syllabus. After that, we learn how to estimate the, say, Young's modulus experimentally, what you do in the lab, and then we solve one or two numericals if possible. So now we learn bulk modulus. What do you mean by bulk modulus? Usually denoted by capital B. It is compression stress by volume strain. 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 So how do we write it? F by A by volume strain delta V by V. Therefore, bulk modulus is Fv by A delta V. This is the formula for bulk modulus. And in fact, say reciprocal of the bulk modulus, that's also very important. What does it mean? How much the substance can be compressed? Compressibility we call. Usually denoted by K, what is 1 by V. Reciprocal of the bulk modulus is called as compressibility. So K equals 1 by V. You must know that whenever it is required, you can use that. So with these ideas, now we just go through bulk modulus once again. It is defined as ratio of compression stress to the volume strain and written like this. F by A is compression stress. In fact, here what type of force acts? Normal force per unit area again. Compression stress means normal force per unit area. Normal force per unit area. Like that. And delta V, change in volume by original volume. So that is what we call as bulk modulus. And its reciprocal is compression stress. Compressibility. And it can be written as A delta V by Fv. That is after reciprocal. Okay, with these things, now we learn how to estimate the Young's modulus in the lab. How to estimate Young's modulus in the lab. Observe, it has an instrument. We learn that instrument now. Look at the board carefully. Say there are two long strings, usually of 2 meter length, suspended from the ceiling of the lab. Usually we do, because 2 to 3 meter length means around 6 to 8 feet it will go. Therefore, we suspend them from the almost ceiling level of the lab. 2 wires are there. Among them, one is experimental, one is standard wire. And say if we take this as experimental wire, this as standard wire for the reference, we fix up a scale there. What we call as main scale. We call it as, you learn it in the lab, main scale. And over this, there's another scale slides, small scale, which is attached to the experimental thing. And this is called as vernier scale. Main scale and vernier scale. And observe, for the main scale, a standard weight is hung, actually suspended. For the vernier scale, that is For the experimental wire, we apply the load, variable load, where we can change the applied load. So this is standard one, this is the thing. This is the experimental setup. This is the experimental setup, what you see in the lab. Sometimes here micrometer screw settings are there. How we measure this, we want to learn. It's a very simple thing. So first we understand there is some arrangement of two scales which will help you to measure around 1/100th of a centimeter or 1/100th of a millimeter, like that, using the combination of two scales. What we call as vernier scale principle that you learn later on in the lab part. But now, first we think of how the experiment is done and what is the formula what we want to use. The experiment is done like this. First of all, without any load to this, we note down a reading. Without any load to this, we note down a reading. We call it as R0. Say we can tabulate the readings like this. Say it is load and reading R0. Load 0, R0 some value. We call it as R0 only. This is reading, I write. R0. Then we increase it to 1K, 2 kg. We note down, say, once we apply a load there, 2 kg load. Usually we apply 5 kg or something like that. Okay. Or sometimes half a kg, 1 kg. That depends on the situation in the lab. Say, once we apply some weight here, what will happen? A force acts on this experimental wire. So because of that, that elongates slightly in millimeter wise. So reading changes. We call that reading as R1. Next, we change the load to next load. We suspend next load, say 4 kg. Again, this elongates a little bit because more load is applied. We call that reading as R2. Likewise, we do it for few more readings. Say 6 kg we apply. We take the reading, observe. As we go on increasing the load here on the experimental wire, it goes on stretching because of the elastic property and deforming force what we are applying in the form of load. So we got these 4 readings we take. Then how do we estimate the Young's modulus? We write the formula first. F by A delta L by L, what we have written in the last session. Or what we can write as F L by A delta L. Now, with this, what is F? The load we applied. In fact, restoring force, that's also equal to load here. So F can be written as M into G, the weight of the load what we apply there. And L, we know the original length. Delta L, how to calculate delta L? Observe, originally R0, then R1. So if we take R1 minus R0, R which is larger, that is to be taken. R1 difference R0 I write. Among R0, R1, which is larger, depending on the scale how we fix. Sometimes R0 may be larger or R1 may be larger. That's why we take the difference. R1 difference R0. Next, that will give us change in length for how many kgs? 2 minus 0, 2 kg length. Next, what we do? R2 difference R1 we do. R2 difference R. The difference in load is 4 minus 2, again 2 kg load. That is again we take delta L1, delta L2. Then R3 minus R2 we do. Delta L3 we call. So for that, observe, if we take the differences like that for those readings, we get change in length for every 2 kg load. 2 kg, 2 kg load difference. Therefore, I can measure the delta L by taking the average of all these things. Delta L for 2 kg load. Once I got all these things, how to measure the area? Area of what? This thin wire. Experimental wire area. Say, how to measure it? There is an instrument. what we call a screw gauge. That screw gauge will help us to measure the radius to 1/100th of a millimeter or so. So very refined instrument, what you learn in the lab when you enter the lab. By using that, we can measure the radius. If you measure the radius, what is the area of the wire? What is the area of the wire? If we measure the radius, what is the area of cross section of the wire? If this is the cylinder, this is the area what I am asking. This is the height means what you say, many of you said pi r square h. That is the volume. In fact, simply area of this wire is required, area of the circle, pi r square only. Area of the circle is pi r square. No, Suhas. It's only pi r square. I'm asking you the area of the circular part, not the curved part. Total area, it's not required because we are applying the force normal to this surface, no? Therefore, this or this one, area of the circular part only required, not the lateral part or something like that. Therefore, pi r square, circular part area. Once you know the circular part area, substitute everything, you'll get the final formula. Young's modulus y equals FL by pi r square delta L. For F also you can substitute mg. This is the formula. mgl by pi r square delta L. This is the formula for Young's modulus what we use in the lab. mgl by pi r square delta L is the formula. You may be asked to explain this in 3 marks question in the board exam. Please write down the question. Write down the question. You need not write this tabular column. For the sake of example, I have given you. Simply down the question. Briefly discuss 3 marks question. Briefly discuss how do you estimate? How do you estimate the Young's modulus? Young's modulus of a wire. Briefly discuss Young's modulus of a wire in the lab. Theory part is only this much. Theory part is only this much. It's very simple. Figure is there in the textbook. If you want, you can write this part, theory part. That is math. With this, we start solving few numericals there, 1, 2 or 3. Today, it may be possible for 2 numericals. And in fact, there's one last part in this chapter. Applications of elastic substances. I hope you can read. I also told you that in between, how the engineers design the ceiling of a room, RCC ceiling, how they use it for the bridges construction, all those things. Just go through that. A very simple idea there. Last part of that chapter. And this, we start solving the numerical. In these numericals, you observe in one of the numerical, you observe how our body is stronger. You will learn it. We do that now. Write down the numerical. Write down the first numerical. Very simple numerical, straightforward calculation. We go for it. A structural steel rod. Structural steel rod. What do you mean by that? A structural steel rod, I'll explain it later on. A structural steel rod has radius of 10 millimeter. Steel rod has a radius of 10 millimeter and a length of 1 meter and a length of 1 meter. Full stop. 100 kilonewton. 100 kilonewton. Force stretches it along the length, along its length. It along its length. Calculate part A, stress, part B, elongation, and part C, strain on the rod. Strain on the rod. Young's modulus given actually. Young's modulus of structural steel, write down next. Young's modulus of structural steel. Young's modulus of structural steel is 2.0 into 10 raised to 11. 2.0 into 10 raised to 11 Newton per meter square. Newton per meter square. So we start solving this now. Observe how do we solve. But what do you mean by structural steel? We learn it. In fact, many times sheer learning these words will help us to get some good idea when we solve MCQs. Structural steel means the steel, what we use for casting the roofs of the house, or the pillars, what we construct for the house construction. They're all we use iron rods, no? They are called as structural steel. And there, 10 mm rod, 8 mm rod, they used to say, whenever you go to such a place, ಅಥವಾ ಎಲ್ಲ ಮನೆಯಿಂದ ಮುಂದೆ ಹೋಗ್ತಾ ಎಲ್ಲರೂ ಕಟ್ತಿದ್ದಾಗ ನಿಂತ್ಕೊಂಡು ನೋಡಿ ಮಕ್ಕಳು ಬಾರ್ಬೆಂಡರ್ಸ್ ಎಲ್ಲ ಇದು ಮಾಡ್ತಿದ್ದಾಗ 10 mm ರಾಡ್ ತಗೋ 8 mm ರಾಡ್ ತಗೋ ಅಂತೆಲ್ಲ ಹೇಳ್ತಿರ್ತಾರೆ. ಈಗ ನಮ್ಗೆ ಆ ಥರದೊಂದು ಸ್ಟೀಲ್ ರಾಡ್ ಅಂದ್ರೆ ಸ್ಟೀಲ್ ಅಂದ್ರೆ ಇಲ್ಲಿ ನಾಟ್ MS, MS ಕೊಟ್ಟಿರ್ತಾರೆ ಅಂದ್ರೆ ನಾರ್ಮಲ್ ಸ್ಟೀಲ್. SS ಅಂದ್ರೆ ಸ್ಟೈನ್ಲೆಸ್ ಸ್ಟೀಲ್, ವಾಟ್ ಯು ಯೂಸ್ ಫಾರ್ ದಿ ಯುಟೆನ್ಸಿಲ್ಸ್, ವಾಟ್ ವಿಲ್ ನಾಟ್ ಗೆಟ್ ರಸ್ಟೆಡ್. ಮನೆಗಳಲ್ಲಿ ಅಡಿಗೆ ಮನೆಯಲ್ಲಿ ನಾವು ಉಪಯೋಗಿಸ್ತೀವಲ್ಲ ಅದು ಸ್ಟೀಲೇ, ಅದು ಸ್ಟೈನ್ಲೆಸ್ ಸ್ಟೀಲ್. SS ಮೆಟಲರ್ಜಿಲಿ ಸೆಕೆಂಡ್ ಇಯರ್ ಅಲ್ಲಿ ಓದ್ತೀರಿ ಮಕ್ಕಳು. ಸ್ಪೈಗಲೀಸನ್ ಅನ್ನೋ ಒಂದು ಇದನ್ನ ಆಡ್ ಮಾಡಿದ್ರೆ ಇಟ್ ಬಿಕಮ್ಸ್ ಅನ್ ಅಲಾಯ್. ಇಟ್ ವಿಲ್ ನಾಟ್ actually behave like normal iron, it becomes stainless steel. That's what we use for utensils in the kitchen. So adena really stainless steel what we use in the kitchen. But ಇಲ್ಲಿ structural steel ಅಂದ್ರೆ casted iron. ಈಗ ಭದ್ರಾವತಿ ಐರನ್ ಸ್ಟೀಲ್ ಫ್ಯಾಕ್ಟ್ರಿ ಮಾಡ್ತೀವಲ್ಲ ಆ ಥರ ಭದ್ರಾವತಿ ಐರನ್ ಫ್ಯಾಕ್ಟ್ರಿ ಐರನ್ ಓರ್ನ ಮೆಲ್ಟ್ ಮಾಡಿ ಈ ಅಲಾಯ್ನ ಆಡ್ ಮಾಡಿದ್ರೆ ಸ್ಟ್ರಕ್ಚರಲ್ ಸ್ಟೀಲ್ ಅಂದ್ರೆ ನಮಗೆ ಕಟ್ಟಡಗಳ ಕಟ್ಟಕ್ಕೆ ಏನ್ ಬೇಕೋ ಅದನ್ನ. ಓಕೆ, ಈಗ ಅದೆಲ್ಲ ಅವ್ರು ಕೊಟ್ಟಿರೋದು ಏನು, ನಮಗೆ ರೇಡಿಯಸ್ ಕೊಟ್ಟಿದೀವ, ಡಯಾಮೀಟರ್ ಕೊಟ್ಟಿದೀವ. ರೇಡಿಯಸ್ 10 mm ಅಂತ ಹೇಳ್ತಿದ್ದಾರೆ ಅಲ್ವೇ. ನೋಡಿ ಬಾರ್ಬೆಂಡರ್ಸ್ ಹತ್ರ ಅವ್ರನ್ನ ಕೆಲಸ ಮಾಡ್ತಿದ್ದಾರೆ ನೋಡಿ, 8 mm ರಾಡ್ ಕೊಡು ಅಂತಾರೆ. 10 mm ಅಂದ್ರೆ ಇದು 10 mm ರಾಡ್ ರೇಡಿಯಸ್. ಸೊ ಇದನ್ನ ಮೀಟರ್ಗೆ ಮಾಡ್ಕೊಂಡ್ಬಿಡೋಣ ಮಕ್ಳು, ಯಾಕಂದ್ರೆ ಎಲ್ಲ ಕಡೆ SI ಯೂನಿವರ್ಸಿಟಿ ಉಪಯೋಗಿಸ್ತಾನೆ ಮೀಟರ್ ಮಾಡ್ಕೊಳ್ಳಿ. ರೇಡಿಯಸ್ ಆಯ್ತು. ಲೆಂತ್ ಕೊಟ್ಟಿದ್ದೀವಿ, ಲೆಂತ್ ಆಫ್ ದಿ ರಾಡ್ ರಾಡ್ ಎಷ್ಟು ಕೊಟ್ಟಿದ್ದೀವಿ. Then we have given force applied 100 kilonewton applied. Length ಎಷ್ಟು ಕೊಟ್ಟಿದ್ದೀವಿ ಮಕ್ಕಳ. Length is given to be 1 meter. Okay. L, F ಗೊತ್ತು, R ಗೊತ್ತು. You are asked to calculate 3 things. Part 1, what is that asked? Stress. We do that first. What is stress? F by area, what we usually denoted by sigma. F by area. F by area, F is 100 kilonewton. They are already given. Kilo means 10 raised to 3 Newton. Divided by area, pi r square. Cross-sectional area of the wire, pi r square. Substitute everything, you'll get the answer. 100, that means 10 raised to 5 in the numerator, because 100 is 10 square, 10 square into 10 cube is 10 raised to 5. Pi is 3.14. R, 10 raised to minus 2, observe. 10 into 10 raised to minus 3, I can write here itself, 10 raised to minus 2 meter. So 10 raised to minus 2 whole square. So how much you get, we'll just do. Observe, when you got powers like this, first simplify the powers. Later on you can go for the calculation. This is 10 raised to minus 4. That means 1 by 3.14, 10 raised to 9 Newton per meter square. Get me the answer for 1 by 3.14. How much it is? 1 by 3.14, most probably nearer 3, nearer 0.3, because 1 by 3 is 0.33. 1 by 3.4, most probably 2.9 or 3. How much is the value for 1 by 3.4? 3.14? 0.318. Okay. Stress is therefore F by A. The sigma stress is 0.318 Newton per meter square. What you can write as Pascal also. Pascal also. So we got this answer. You just check. Now, once you know these things, second one is asked is what? What is that? Part B, elongation. Part B, en kelidibi, elongation. Delta L is asked. How do we calculate delta L? For that we have given Y also. Y for the structural steel, 2.0, 10 raised to 11 Newton per meter square is given. Structural steel along Young's modulus. So to calculate delta L, I write Young's modulus formula. Stress by strain means delta L by L. Sigma, instead of writing F by A, we have 10 more minutes to go. We'll see. Most probably we can conclude this and then we start with the other numerical also slightly. Stress, sigma is stress divided into L by delta L. So delta L can be written as sigma L by Y. Substitute everything. Sigma is 0.318, L is 1 meter, Y is 2, 10 raised to minus 11. Say plus 11, sorry. Plus 11, not minus 11. So it is easy to calculate without calculator. 0.21, 2.5, 2.9, 0.159, 10 raised to minus 11 meters. Very much smaller, very much smaller. Okay. Point Young's modulus to be taken. So 0.15 we are getting after dividing it. So final answer is, if we write it in, say, standard form, 1 to minus 12 I have to write. Minus 12 meter. Very, very small thing. Very small thing. You calculate this strain. In fact, one of you said, I have forgotten here, say Young's modulus, sigma, for which I have not written the power there. I have to write, sorry, 10 raised to 9 it is. So now the change is here. I have to take 0.318, 10 raised to 9 into 1. So 10 raised to 9 means plus 11 minus 9 is minus 2 there. Minus 2 there. So 1.59 minus 3. That is 1.59 millimeter is the answer. Sorry. I have left that 9 there. One of you actually hinted at that to me. So thank you for correction. 1.59 10 raised to minus 3 meters. That is 1.59 millimeter. Observe, can you see the big thing what you are seeing here in the answer? That structure is steel, 10 mm broad, what we use for casting the roofs or something. How much it expands? Just observe. Hardly 1.5, 1.6 millimeter. When you apply a load of 100 kilonewton, that is 10 raised to 5 Newton, a large force is applied, but its elongation is very, very small, hardly 1.6, 1.5 millimeter. In your scale, a small division and a half there, very, very small. That's why we make use of them for the construction purpose, because once we construct the ceiling and many floors on the house, actually, how much force it has to withstand because of that. So it can withstand so much of force with a slight elongation, 1.59, 10 raised to minus 3 meters. So that is the idea. What else asked? Last thing, strain. Last strain is created, delta L by L you apply. What is that last part? Delta L is how much? What we have calculated is 1.59, 10 raised to minus 3 by 1 meter. So 1.59, 10 raised to minus 3, no unit, no unit. That is the strain. If you write it in normal form, 0.00159, so much smaller. So we can conclude this numerical here. Once you have written strain and other things, we go for, say, as we said on that day, rubber is less elastic compared to steel. Why? We want to learn now quickly, because by the time we may end this session, we say rubber is less elastic compared to steel. Why we feel like that? Because, say, normal day-to-day life ಯೋಚನೆ ಮಾಡಿದ್ರೆ ಹಿಂಗೆ ಎಳೆದಟ್ಟಿಗೆ ರಬ್ಬರ್ ತುಂಬಾ ದೊಡ್ಡದಾಗಿ ಹಿಂದಕ್ಕೆ ಬರೋದ್ರಿಂದ we may take it as more elastic. Not like that. In fact, rubber is elastomer. Elastomer means stress and strain are not directly proportional. On that day, I told you, they can elongate to large extent. ಅದರಿಂದ ಹಾಗೆ ಹೇಳಕ್ಕಾಗಲ್ಲ. ಒಟ್ಟಿನಲ್ಲಿ ಎಲಾಸ್ಟಿಕ್ ಯಾವುದು ಅಂತ ಕಲಿಬೇಕು. Y equals what we have written, F L by A delta L we have written. For the given force, for the given area, for the given length, for which substance delta L is the least, that is more elastic. Observe, you take a rubber band there and you take a steel wire there. If you apply 1 Newton force to them, it elongates very much larger. Delta L is very large. This will not elongate to large extent. Just now we applied 100 kilonewton, we got only very small, 1.5 or 1.6 millimeter. It's almost very small. Observe, if all these three things are same, delta L is least for steel, therefore Y is larger. That's why we say, for which Young's modulus is largest, that is more elastic. More elastic. Not in common sense. A common sense tells which elongates more, that is more elastic. Not like that. But rubber cannot become compared with that, because rubber is an elastomer. Elastomers, they can take large strain and they can come back. But stress is not directly proportional to strain. That's why in our textbook, stress versus strain curve for elastomers given, stress versus strain curve for elastomers given like this. Say they have given like this. Our aorta, say, which is connected to our heart. Aorta, that is heart part, is an elastomer because it has to expand, compress many, many times. 1 second ಗೆ 72 ಸರಿ compress ಆಗಬೇಕು, expand ಆಗಬೇಕು. So such things, even rubber comes under this category. On that day, Adruta asked me, most probably rubber. Now I am saying you. Elastomers they are, but the graph for stress versus strain is like this for elastomers. So with these things now, next idea is to start with one more numerical. If time permits, I just dictate that numerical, or you can Write down that. Most probably 1 or 2 minutes left. By that, we write down the numerical. Next class we solve. Let's not solve it now. Just finish up the writing by that time. Write down one numerical. A copper wire of length. ಅಕಸ್ಮಾತ್ ಮಧ್ಯದಲ್ಲಿ ಮುಗಿದ್ರೆ ಟೈಮು ನಿಲ್ಲಿಸ್ತೀನಿ ಮಕ್ಕಳ, ತೊಂದರೆ ಇಲ್ಲ, ಮತ್ತೇನು ಸ್ಟಾರ್ಟ್ ಮಾಡಲ್ಲ ಮೀಟಿಂಗ್. A copper wire of length 2.2 meter. A copper wire of length 2.2 meter. It's example 9.2 in your text. 236 page number. ಇಲ್ಲಿ ಬರ್ಕೊಂಬಿಡಿ ಹೇಳ್ತೀನಿ, ಹೆಂಗಿರೋ ಟೈಮ್ ಇದೆಯಲ್ಲ. A copper wire of length 2.2 meter and a steel wire of length 1.6 meter. And a steel wire of length 1.6 meter, comma, both of diameter 3 millimeter, 3.0 millimeter they have given for the sake of precision, 3.0 millimeter are connected end to end, when stretched by a load